Welcome back. In this video, you'll learn about Taylor polynomials and approximations. Let's get to it. Alright, so Taylor polynomials are part of a Taylor series, and we can use them to approximate values for a function. Alright, so remember that this is the form of a Taylor series centered at C, and that Taylor series represents a function f of x. So we have f of x is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial times the quantity x minus c to the power of n. And of course, if c is equal to 0, then this Taylor series becomes a Maclaurin series. A Maclaurin series is just a Taylor series centered at 0. Alright, but the terms of a Taylor series look like this. The first term where n equals 0 is just the function evaluated at c. Then the next term, where n equals 1, we have the first derivative of our function evaluated at c times the quantity x minus c. Then our next term, where n equals 2, we have the second derivative evaluated at c times the quantity x minus c squared. And that's all divided by 2 factorial. And then of course the terms would continue on forever because a Taylor series starts at n equals 0 and goes on to infinity. But I decided to highlight one more term, which is the nth term of a Taylor series, where we have the nth derivative evaluated at c times the quantity x minus c to the power of n divided by n factorial, and then there's more terms from there. Okay, and so that is what the terms of a Taylor series look like, and it's important to understand that these terms of the Taylor series represent a function f of x. And if it were possible to write out all of these terms from n equals 0 to infinity, all of those terms added together would equal that function f of x. And so, if you wanted to find the value of a function, f of x, at a particular value of x, you could plug in that value of x into all of these terms of the Taylor series from n equals 0 to infinity, and you would be able to find that exact value for the function. However, from a realistic standpoint, we really can't do that. We can't add up terms forever. You would die before you could add up all of those terms. And so the terms of a Taylor series aren't very useful for finding an exact value of a function. Instead, they're going to be useful for approximating the value of a function at a particular value of x. Right? And so what we have to do is add up the terms of a Taylor series evaluated at a particular value of x until a certain point. We're going to cut off the terms at some point of our choosing. All right, and that point of our choosing I'm just going to represent with the nth term. Right? We would just decide to stop adding terms from our Taylor series at some nth term. Whatever that value of n is up to us. Okay, and since we're cutting off all of the other terms after that nth term, evaluating these terms at that value of x is only going to be an approximation of the value for our function, right? We would need all of the terms to have the exact value, so if we cut off some of those terms, what we're left with is just going to be an approximation. And the more terms that we decide to include in that approximation will improve the accuracy of that approximation compared to the actual value, right? The more and more terms that you decide to add, the closer you will be to the actual value, which would be found by adding all of the terms from 0 to infinity, which you can't do. Okay, and so the moment that we stop adding terms from our Taylor series, we cut it off at a certain point at the nth term. What we have with those terms is no longer a Taylor series, but rather a Taylor polynomial to the nth degree. And we represent that with the following notation. A Taylor polynomial of degree n, we represent with capital P sub n, and then we have of x, is equal to the sum from k equals 0. I'm using k instead of n because we don't want to confuse that with the value of n that we are going to be adding up to, right? We're going to be starting at the value of 0, and we're going to stop at the value of n, which determines the last term from the Taylor series that we're going to use, and then we have the expression that represents our Taylor series. All right, so what this is saying is that from 0 to some value n, we are going to be adding up the terms of a Taylor series. But since this doesn't go on forever, we stop at some value n. This doesn't represent the Taylor series, it represents a Taylor polynomial, specifically of degree n. All right, and just a quick side note, if c is equal to 0, this would become a Maclaurin polynomial instead of a Taylor polynomial because, like I said earlier, a Maclaurin series is just a Taylor series centered at 0. So if c is equal to 0, this would be a Maclaurin polynomial. All right, but putting that aside, let's take a look at what the first couple Taylor polynomials would look like. Here I have the first degree, second degree, and third degree Taylor polynomials. The first degree is where n equals 1, the second degree is where n equals 2, and the third degree is where n equals 3. When n equals 1, what that says is that for that Taylor polynomial to the first degree, we're only going to have the terms from the Taylor series up until the n equals 1 term. So we have our n equals 0 term, which is f of c, and then we add that to the n equals 1 term, where we have the first derivative evaluated at c times the quantity x minus c. Now for every degree after that, we're just going to be adding on one more term to that polynomial, right? So a second degree Taylor polynomial, where we have p sub 2 of x, that's going to include those first two terms that a first degree Taylor polynomial had, but then we're going to add on one more where n equals 2. That is where we stop. There are no more terms after that last term for a Taylor polynomial. It's not a Taylor series. It stops with the term for the specific value of n that is described by the degree of the Taylor polynomial. All right, so the second degree Taylor polynomial ends with f double prime, or the second derivative, evaluated at c, times the quantity x minus c squared divided by 2 factorial. And then the third degree Taylor polynomial will end with the term where n equals 3. So we include those three terms from the second degree Taylor polynomial, but then we add on one more where n equals 3. So we have the third derivative evaluated at c times the quantity x minus c cubed divided by 3 factorial. All right, and so we could continue on from here. We could have a fourth degree Taylor polynomial, a fifth degree Taylor polynomial, a sixth degree, and so on. All we would have to do to find those Taylor polynomials is just keep adding on one more term from the Taylor series. All right, and so now let's take a look at an example of a function and see if we can find the first couple Taylor polynomials. Okay, so here we have that our function f of x is equal to the natural log of x, and we're going to find some Taylor polynomials for this function where those polynomials will be centered at c equals 1. And so let's start by just finding the first degree Taylor polynomial for this function. Now remember, the terms of our Taylor series look like this, starting with n equals 0, then n equals 1, n equals 2, and so on. And so if we want the first degree Taylor polynomial for our function, all we need are these first two terms, the n equals 0 term and the n equals 1 term, right? The first degree Taylor polynomial is going to stop at the term where n equals 1. So we're going to need to evaluate our function at the value of c, and we're going to need to evaluate the first derivative of our function at the value of c as well. All right, so remember, f of x is equal to the natural log of x, and the derivative f prime of x will be equal to the derivative of the natural log of x, which we know is 1 divided by x. All right, so the first degree Taylor polynomial will look like this. Our first term is f of c, or our function evaluated at 1. That's our value of c. So we're going to have the natural log of 1, and then we're going to add that to the derivative evaluated at c times x minus c. So our derivative is 1 divided by x, and so we have 1 divided by 1, right? 1 is our value of c. So we plug that value of 1 in for x, and then we're going to multiply by x minus c, which is 1. Okay? Now the natural log of 1 is equal to 0, so our first degree Taylor polynomial will be equal to 0 plus 1, because 1 divided by 1 is 1, times x minus 1. All right, but 1 times x minus 1 will just be x minus 1, so our first degree Taylor polynomial for the natural log of x will just be x minus 1. That is all there is to our first degree Taylor polynomial. Now if we want to find the second degree Taylor polynomial, we'll have capital P sub 2 of x is equal to all of the terms of our first degree Taylor polynomial. So we're going to include x minus 1, but then we're going to add the next term from the Taylor series, where n would equal 2. But in order to write out that term, we need to know the second derivative of our function. So let's find that. We know that the first derivative is 1 divided by x, and that is the same as x to the power of negative 1, right? We can move x to the numerator, and doing so makes that exponent negative. So we went from +1 to -1. And now we can use the power rule for derivatives and find that f double prime of x is equal to -x to the -2nd power, which is the same as -1 divided by x squared, right? We multiply that exponent of -1 down, so we have -x, and then we subtract 1 from the exponent, so we have -2, and then moving that x to the -2nd power to the denominator makes that exponent positive. And so the n equals 2 term will look like this. We're going to have a second derivative evaluated at c, which is 1. So we're going to have -1 divided by 1 squared, and that's going to be multiplied by x minus c, which is 1 squared divided by 2 factorial. Now if we simplify, -1 divided by 1 squared is just 1, so we have -1 divided by 1. So this is just going to become -1. That is the value of our second derivative evaluated at 1. And then 2 factorial is just 1 times 2. So 2 factorial is equal to 2. So I'll rewrite that to be 2. And then we can just move this negative out front and rewrite this so that the term is just negative. And so our n equals 2 term will be x minus 1 squared divided by 2. So let me just make that look a little bit nicer. That last term for our second degree Taylor polynomial will be x minus 1 squared divided by 2. Okay, so that is our second degree Taylor polynomial. We have found the first degree Taylor polynomial and the second. Now let's do one more. Let's find the third degree Taylor polynomial. The third degree Taylor polynomial will include all of the terms from the second Taylor polynomial, but we're going to add one more, specifically the term where n equals 3. So we're going to have x minus 1 minus x minus 1 squared divided by 2, and then we're going to add that to the n equals 3 term, which will require that we know the third derivative, right? We want to find the third derivative evaluated at c times x minus c to the power of 3 divided by 3 factorial. That is going to be our n equals 3 term. Now to find the third derivative, we need to take the derivative of our second derivative. So if we use the power rule for derivatives, we'll multiply that -2 down and then subtract 1 from the exponent. So we'll have f triple prime of x is equal to +2 times x to the -3rd power, which is equal to 2 divided by x cubed, right? -2 times the -1 is +2, and then subtract 1 from -2, and you have -3, and then moving x to the power of -3 to the denominator makes that exponent positive. So this is our third derivative, and if we evaluate that at c, like we need to do for this term, our value of c is 1, so we have 2 divided by 1 cubed. That's just going to be 2 divided by 1, which is 2. So I'll replace f triple prime of c with what it's equal to, which is 2, and then we have x minus c cubed. That will be x minus 1 cubed, because c is equal to 1. So I'll rewrite this. We'll have x minus 1 cubed. And then 3 factorial, that is the same as 1 times 2 times 3, right? So we'll have 1 times 2 times 3, that's 3 factorial. But 1 times 2 is 2, and we have a 2 in the numerator. And so those are going to cancel out. And so we're just going to be left with x minus 1 cubed divided by 3. All right, so I'm just going to rewrite this term. And what we will have is x minus 1 cubed divided by 3. And right here, we now have the third degree Taylor polynomial for our function, the natural log of x. All this third degree Taylor polynomial is the first couple terms of a Taylor series up until the n equals 3 term. All right, and so building Taylor polynomials isn't all too bad. As long as you know what the terms of a Taylor series look like, you can continually create more and more Taylor polynomials by just adding another term for each value of n. Okay, and so now what we could do with these Taylor polynomials is choose a value of x that we would want to approximate for the natural log of x, typically a value that's close to our value of c, and plug that into these Taylor polynomials. And with each polynomial, from the first degree to the second degree to the third degree, that approximation would get better. The approximation would probably not be so good for the first degree Taylor polynomial, but it would get better with the second degree Taylor polynomial, and then it would get even better with the third degree Taylor polynomial, because we keep on adding more and more terms from the Taylor series, which if you had all of the terms would accurately represent the value of a function for a particular value of x. All right, but before we look at an example of that, we first need to discuss what the error will be for that approximation. All right, and so to discuss the error associated with approximating values using Taylor polynomials, we need to remember that a Taylor polynomial is only part of a whole Taylor series, right? All of the terms from n equals 0 to infinity for a Taylor series represent a function f of x, and so if we cut off those terms at a certain point and create a Taylor polynomial and evaluate a Taylor polynomial at a value of x, that value will only be an approximation. And of course, like I said earlier, the higher the degree of the Taylor polynomial, the better that approximation will be. But since we cut it off at a certain point, we're not going to get an exact value. We will get an approximation, and that approximation is going to be off by some value that we call the error, or sometimes you will hear it called the remainder. And we represent the error with the following notation. Error will be equal to capital R sub n of x. We use capital R because it represents remainder rather than error, but it means the same thing. The remainder and the error are the same concept, and we're going to be taking the absolute value of that remainder or of that error, because we're only interested in the difference between our approximation and the actual value, not if our approximation is below or above, right? We don't care about the sign. We just want to know what that difference is between the actual and the approximation, so we take the absolute value of our error. And what that error is equal to is the absolute value of the difference between the actual value of the function at a particular value of x and a Taylor polynomial of degree n. Right, so the Taylor polynomial of degree n at a value of x is an approximation of the actual value of our function at x, and so the difference between the actual and the approximation will be the remainder, or you could view it as the error. All right, and so subtracting the approximation from the actual value would give you the exact error or the exact remainder, but there's going to be circumstances where we don't know the actual value, and so what we have to do is approximate that remainder or approximate that error. And so typically what we want to find is an error bound, or the maximum error associated with the approximation from the Taylor polynomial. And that is what capital R sub n of x will actually represent. That's what we're typically going to calculate, and we can find that by using the following formula. Capital R sub n of x will be equal to the absolute value of the n plus 1 derivative of some value z, which we'll talk about in a little bit, times the quantity x minus c to the power of n plus 1 divided by n plus 1 factorial. All right, and so essentially all this is the next term of the Taylor series after where we stopped for the Taylor polynomial, right? Whatever that value of n is for the Taylor polynomial, we're going to look at the next term from the Taylor series, and that's going to help us determine the error or remainder. All right, now the proof for this formula, or the reason why this is true, is a bit beyond the scope of what you need to know for Calc 2. So I'm not going to show that to you explicitly. It's not necessary to understand in order to use the formula. All you need to know is that the maximum error, or the maximum remainder, that comes from using a Taylor polynomial to approximate a value for a function is that it's equal to the absolute value of the n plus 1 term from the Taylor series. All right, the only thing that's a little bit different is this value of z, and this value of z that we're going to plug into the n plus 1 derivative is going to be between the value of x and c. All right, so either x will be less than z, which is less than c, or c will be less than z, which is less than x. Either way, z is between those two values of x and c. And x is going to represent the value that we want to approximate, and c is going to represent a value close to the value of x that we do know the value of. All right, and so when choosing the value of z that we're going to actually plug into that n plus 1 derivative, you're going to want to set it equal to the value of x or c, depending on which is going to give you the largest error, because we don't want to ever underestimate our error. We would rather overestimate it instead. That's why we want the maximum error. So we're always going to be looking to create the largest error possible based on our values of x and c. And so that's what z is going to be equal to. Z is just that value that is going to give you the largest error. All right, now that might not quite make sense right now, but we're going to look at an example where you can see this error formula in action. All right, and so let's take a look at that example now. Okay, so here's our example. We want to find the third degree Taylor polynomial for f of x is equal to the natural log of x centered at c equals 1 in order to approximate the natural log of 1.1. All right, now we already completed half of this problem with our example from earlier, right? We already found the third degree Taylor polynomial for the natural log of x centered at c equals 1. It looked like this. We had p sub 3 of x is equal to x minus 1 minus x minus 1 squared divided by 2 plus x minus 1 cubed divided by 3. All right, so that part of our problem has already been done. We did it before. Now what we want to do is use this Taylor polynomial to approximate the natural log of 1.1, and then we're going to calculate the error of that approximation. Okay, so it's important to realize that this Taylor polynomial, this third degree Taylor polynomial, is centered at c equals 1. And what that tells us is that this Taylor polynomial will approximate our function, the natural log of x, around the value of 1. All right, so we can use this Taylor polynomial to approximate values close to 1 for the natural log of x, and that's it. We don't want to use this to approximate values that are a lot bigger than 1 or a lot smaller than 1. We want to use it for values close to 1, like 1.1. Right? We're going to use this to approximate the value of the natural log of 1.1. If we wanted to approximate the value of the natural log of 2.1 or 3.1, we would want a Taylor polynomial centered at a different value. For 2.1, we would want to center it around 2. For 3.1, we would want to center it around 3. All right, so that's the reason why you would want to center a Taylor polynomial at a certain value of c. It's going to allow you to approximate values near that value. Okay, so in this case, our value of x, the value that we want to approximate, is 1.1, and c is equal to 1, which is the value that is close to the value that we want to approximate. And so let's approximate the natural log of 1.1. That is going to be equal to the third degree Taylor polynomial evaluated at 1.1. We're going to plug 1.1 into this polynomial. So this is going to be equal to 1.1 minus 1 minus 1.1 minus 1 squared divided by 2 plus 1.1 minus 1 cubed divided by 3. Now, each of these quantities where we have 1.1 minus 1, that's just going to be 0.1, right? 1.1 minus 1 will be 0.1. So this is equal to 0.1 minus 0.1 squared divided by 2 plus 0.1 cubed divided by 3. Now, if you plug this into your calculator, what you'll find is that our approximate value will be 0.095333 and some more decimals. All right, and now just for comparison, you can plug the natural log of 1.1 into your calculator and see that the actual value is 0.0953118 and some more decimals. And so you can see that the third degree Taylor polynomial gives us an approximation that's pretty close to the actual value, at least to 4 decimal places, right? 0.0953 matches up with 0.0953. Okay, now assuming we don't know what that actual value is, now what we want to do is determine the maximum error that is associated with this approximation. All right, if we wanted to, we could find the exact error by just subtracting our approximation from the actual value that I showed you. But instead what we're going to do is find the maximum error or the error bound for our approximation. All right, so I'm going to box this in so we know that that is our approximation. And now if I clean up my work, what we want to do to find the maximum error or the error bound is use our formula for the maximum error. R sub n of x is equal to the absolute value of the n plus 1 derivative evaluated at z times the quantity x minus c to the power of n plus 1 divided by n plus 1 factorial. All right, now in this case, our value of n is going to be 3, right? Because we wanted to find a third degree Taylor polynomial to approximate this value, we found that third degree Taylor polynomial where n was equal to 3. So this n for our remainder or our error will also be 3. So what we're really looking for here is r sub 3 of x, which will be equal to the absolute value of the n plus 1 derivative. So that's going to be 3 plus 1. So we're looking for the fourth derivative evaluated at z. So we'll have the fourth derivative of z times x minus c to the power of 4, right? N plus 1 is 3 plus 1, which will be 4. and then we're going to divide by 4 factorial. All right, so this is the equation or the formula that we're going to use to calculate our error. Now we know what x is equal to, it's 1.1, and we also know c is equal to 1, but what about z? Well, remember, z is between x and c. Now in this case, c is the smaller value of 1, and x is the larger value of 1.1, so z is between 1 and 1.1, and we want to choose either 1 or 1.1 to be z based on which of these values is going to make this error the greatest. And in order to figure that out, we first need to know what that fourth derivative of our function is. And whatever value of z, whether it be 1 or 1.1, makes that fourth derivative the biggest, ignoring the sign because we're going to take the absolute value, that is the value of z that we want to use for the error calculation. That will ensure that we are calculating the maximum error or the error bound. All right, but first we need to find that fourth derivative. If you remember from our work from earlier, we found that the third derivative of the natural log of x was equal to 2 divided by x cubed, and that was equal to 2 times x to the power of negative 3. If we take the derivative again, the fourth derivative of x will be equal to negative 6 times x to the power of negative 4, which is equal to negative 6 divided by x to the power of 4. Right, we multiply that exponent down, negative 3 times 2 is negative 6, and then subtract 1 from the exponent to get negative 4, and then we move x to the power of negative 4 to the denominator, which makes the exponent positive. Now if we plug 1 and 1.1 into this fourth derivative, which of those values will make this derivative the biggest, not taking that negative sign into account? All right, because that negative sign is going to be removed when we take the absolute value of that fourth derivative. All right, so if we plug in 1 into this denominator, we'll have 1 to the fourth power in the denominator. And if we plug 1.1 in, we'll have 1.1 to the power of 4. All right, now 1.1 to the fourth power is going to be bigger than 1 to the fourth power, right? 1 to the fourth power is just 1, but 1.1 to the fourth power will be bigger than 1. And when your denominator gets bigger for a fraction, the value of that fraction gets smaller. So we don't want to use 1.1, we want to use 1. Because the smaller your denominator is, the larger the value of your fraction, which means that the value of our fourth derivative is also going to get bigger. So we want to use 1 for our value of z, not 1.1. Okay, so if I clean up my work here, let's calculate our error. This is going to be equal to the absolute value of our fourth derivative evaluated at z, which is going to be negative 6 divided by 1 to the power of 4, times x minus c, which we know x is 1.1 and c is 1, so we'll subtract 1 to the power of 4 divided by 4 factorial, which is 1 times 2 times 3 times 4. All right, now 1 to the power of 4 is just 1, and these absolute value bars are going to eliminate that negative, so what we're going to be left with is 6 times 1.1 minus 1, which is 0.1 to the power of 4, divided by 1 times 2 times 3 times 4. But now 1 times 2 times 3 is 6, right? 1 times 2 is 2, 2 times 3 is 6. So 1 times 2 times 3 will cancel out with 6, so we can cross those out. And what we're left with is 0.1 to the power of 4 divided by 4. And if you plug that into your calculator, you will get the following result of 0.000025. That right there is the maximum error for our approximation of the natural log of 1.1. This approximation is at most 0.000025 off from the actual value of the natural log of 1.1. All right, and so that is how you can approximate a value for a function using Taylor polynomials, and how you can find the error of that approximation as well. And so before we end this lesson, let's look at one more example of going through this whole process one more time. All right, so here's our example. We want to find the second degree Taylor polynomial to approximate the square root of 16.1 and calculate the error for that approximation. All right, so in this case, our function, f of x, is going to be equal to the square root of x, right? We want to approximate the square root of 16.1, and so really what we're doing is approximating the square root of x at the value of 16.1. All right, so x is equal to 16.1. That is the value that we want to approximate. And so if we want to approximate 16.1, what value of c should we use for our second degree Taylor polynomial? What should we center our polynomial around? Well, since we want to approximate 16.1, we should pick a value close to 16.1. In this case, that would be 16, right? We should let c equal 16 because then we will create a second degree Taylor polynomial centered at 16, which will allow us to approximate values for that function close to that value of 16. All right, so if you're not explicitly told where to center your Taylor polynomial, that is how you can determine what that value of c will be. You look at the value that you want to approximate, which was 16.1, and pick a value close to that, preferably a value that you do know the value of when you plug it into your function. In this case, we do know that the square root of 16 is equal to 4, so 16 was a good choice for c. All right, now in order to find the second degree Taylor polynomial for this function, we are going to need to take at least two derivatives, right? Because a second degree Taylor polynomial will have the terms from the Taylor series up until the term n equals 2, where we will have the second derivative evaluated at c. So let's start out by just finding the second derivative of our function. So first, we need to find the first derivative. So f prime of x will be equal to the derivative of the square root of x. Now remember, the square root of x is equal to x to the power of 1/2. That is the same thing as the square root of x. So if we use the power rule for derivatives, we'll multiply 1/2 down and subtract 1 from that exponent. So we'll have 1/2 times x to the power of negative 1/2, right? 1/2 minus 1 is negative 1/2. And of course, we could rewrite that to be 1 divided by 2 times the square root of x. All right, we can move x to the power of negative 1/2 to the denominator to have x to the power of positive 1/2, which is the same as the square root of x. Okay, now the second derivative, f double prime of x, will be equal to the derivative of the first derivative. So we'll multiply the exponent down and subtract 1 from that exponent. So we'll have negative 1/4 times x to the power of negative 3/2. All right, negative 1/2 times positive 1/2 is negative 1/4, and negative 1/2 minus 1 is negative 3/2. Okay, and if we rewrite that, that will be equal to negative 1 divided by 4 times x to the 3/2 power. All right, so I moved x to the power of negative 3/2 to the denominator, so now we have x to the power of positive 3/2. Now we can stop there with the second derivative for the second degree Taylor polynomial. However, when we go to calculate the error, we're going to need to know the third derivative, right? Remember that error formula includes the derivative of n plus 1, where that n comes from the degree of the Taylor polynomial that we want to find. So since we want the second degree Taylor polynomial to approximate this function at 16.1, we're going to need to know the third derivative in order to calculate the error. All right, so I'm going to calculate this for later, and we'll save it to use with our error formula. But the third derivative, f triple prime of x, will be equal to the derivative of our second derivative. So if we multiply that exponent down, we'll have 3/8 times x to the power of negative 5/2 if we subtract 1 from that exponent, right? Negative 3/2 minus 1 is negative 5/2, and multiplying this exponent down, we have negative 3 times negative 1, which is positive 3, and then 2 times 4, which is 8. And we can rewrite the third derivative to be 3 divided by 8 times x to the power of 5/2. All right, so I just moved x to the power of negative 5/2 to the denominator, which makes that exponent positive. All right, now if I clean up my work here, we now have our first three derivatives for our function f of x, and so now we can find the second degree Taylor polynomial for this function. But in order to do that, we need to first evaluate the function, the first derivative, and the second derivative at the value of c. And so our value of c is 16, and so let's start with the original function. F of 16 is equal to the square root of 16, which is equal to 4. Then our first derivative, f prime of 16, will be equal to 1 divided by 2 times the square root of 16, which is equal to 1 divided by 2 times 4, which is equal to 1/8. Then for the second derivative, we'll have f double prime of 16, which is equal to negative 1 divided by 4 times 16 to the 3/2 power. Now the 3/2 power is the same as taking the square root of this value and then cubing it, right? Because we could rewrite this as 16 to the 1/2 power cubed. because you would multiply those exponents to get 3/2 as the exponent of 16. So the square root of 16 is 4, so we have 4 to the power of 3, and 4 cubed is 64. So what we have here is that this is equal to -1 divided by 4 times 64, and 4 times 64 is 256. So this is equal to -1 divided by 256. All right, now we don't need to evaluate our third derivative at that value of c, at least not yet. Maybe we will when we go to calculate the error, but that's going to depend on whether 16 or 16.1 will give us the bigger error. All right, but we'll worry about that later. For now, we just want to find our second degree Taylor polynomial. So if I clean up my work, our second degree Taylor polynomial will look like this. We'll have p sub 2 of x is equal to f of 16 plus f prime of 16 times x minus c, or I guess I could write that as x minus 16, since our value of c is 16. So we have x minus 16, and then we'll have one more term for the n equals 2 term, where we have the second derivative. So we'll have f double prime of c, which is 16, times x minus 16 to the power of 2, or x minus 16 squared, divided by 2 factorial. All right, now if we plug in those values that we know, we'll find that the second degree Taylor polynomial is equal to 4, right? F of 16 is 4, plus f prime of 16, which is 1/8, times x minus 16, plus f double prime of 16, which is -1 divided by 256. I'm going to write that on the outside. We'll have -1 divided by 256 times x minus 16 squared divided by 2 factorial, which is 1 times 2, which is just 2. All right, now if we simplify, this will be equal to 4 plus 1/8 times x minus 16 minus x minus 16 squared, right? I'm just going to move this negative out front, make this whole term negative, and then 1 times this quantity will just be x minus 16 squared. And then in the denominator, we have 256 times 2, which is 512. So we will divide by 512. All right, and so now what we have right here is the second degree Taylor polynomial centered at 16 for the square root of x. This is what we want to use to approximate the value of the square root of 16.1. Okay, so now at this point, we don't need any of this other work. All we need is our third derivative that we will use for our error and this second degree Taylor polynomial. So if I clean up my work, let's calculate our approximation. We need to approximate the square root of 16.1, and the square root of 16.1 will be equal to our second degree Taylor polynomial evaluated at 16.1, and that's going to be equal to 4 plus 1/8 times 16.1 minus 16 minus 16.1 minus 16 squared divided by 512. Now 16.1 minus 16, we have that right here and here. That's just equal to 0.1. So this is equal to 4 plus 1/8 times 0.1 minus 0.1 squared divided by 512. All right, now if you plug that into your calculator, this will be equal to 4.012480468 and some more decimals. Now it's important to remember that this is an approximation, so it's probably more accurate if I rewrote this equal sign as an approximate sign, right? The square root of 16.1 is approximately equal to 16.1 plugged into our second degree Taylor polynomial. I probably should have used an approximation sign for our example earlier. The natural log of 1.1 would have been approximately equal to the third degree Taylor polynomial evaluated at 1.1. All right, I think it was clear that what we got was an approximation, but it's always good to make sure you write approximately equal to in your work so that whoever's looking at your work knows that you understand that it's an approximation, not an exact value. Because if we compare this approximation to the exact value of the square root of 16.1, the actual value is 4.012480529 and some more decimals. So you can see that this approximation is actually pretty close to the actual value, at least for the first 6 decimal places, right? 0.12480, those all match up. And so our approximation is pretty good, but we still want to know the error. If we wanted to know the exact error, we could subtract our approximation from that actual value that I showed you. But what we want to calculate here is the maximum error or the error bound. And so in order to do that, we need to use our error formula. So if I clean up my work, in this case, the error that we want to calculate is r sub 2 of x, right? Because we wanted a second degree Taylor polynomial. Our value of n was 2, and so we want to find r sub 2 of x, which means that we want to calculate the absolute value of the n plus 1 derivative evaluated at z, and n plus 1 will be 2 plus 1, which is 3, and we already found our third derivative, so we're good there, but I'm going to write it out like this. We're going to have f triple prime, the third derivative, of z times x minus c cubed divided by 3 factorial. All right, so remember, we're just looking at the next term of the Taylor series after we stopped for our Taylor polynomial, where n is equal to 3. That is what r sub 2 is equal to. Now in this case, what should our value of z be? Z is always between x and c. In this case, c is the smaller value and x is the larger value. So we know that z is between 16.1 and 16, but which of these values will result in a larger value for our third derivative? Well, just like with our other example, we have a rational function or a fraction where x is in the denominator. And so when you have a value in the denominator, the bigger that value is, the smaller the value of the fraction will be. So 16.1 raised to the power of 5 halves is going to be bigger than 16 to the power of 5 halves, right? Because 16.1 is a bigger number, that's going to make this denominator bigger, which would make the value smaller. So we don't want to use 16.1 for z, we want to use 16, which will make the denominator smaller, which will result in a larger value for our third derivative. So we're going to use 16 as our value of z, and so let's just plug that in. Let's find out what that is. F triple prime of z is equal to 3 divided by 8 times 16 to the power of 5 halves. Now 16 to the power of 5 halves could be rewritten to be 16 to the 1/2 power to the 5th power, right? We multiply those exponents and have 5 halves as the power of 16. And 16 to the 1/2 power is the square root of 16, which is just 4. So you have 4 to the power of 5, and 4 to the 5th power is 1024. So what we have is that this is equal to 3 divided by 8 times 1024, and 8 times 1024 is 8,192. So this is equal to 3 divided by 8,192. Okay, so now that we know what our value of f triple prime of z will be, let's plug that into this error formula, as well as our value of x and c. And what we'll find is that this is equal to the absolute value of 3 divided by 8,192. I'm just going to move that to the outside and multiply it by the rest of the expression. So we'll multiply this by x minus c, which will be 16.1 minus 16 cubed. And I'm just going to erase this work now that we already wrote down what f triple prime of z is. And then that is divided by 3 factorial, which is 1 times 2 times 3. Now this 3 is going to cancel out with this 3, so I'll cross those out. And then what we're left with in the denominator is 8,192 times 1 times 2. So we just have 2 times that value. And then 16.1 minus 16 is 0.1. And there's nothing negative in here, so these absolute value bars can be removed. And what we'll have is that this is equal to 0.1 cubed divided by 16,384. That's what 2 times 8,192 will give you. All right, now if you plug this into your calculator, that will be equal to 0.0000006. Okay, so that's 7 zeros, in case it's hard to count how many I wrote down. But if you wrote that in scientific notation, if your calculator is capable of doing that for you, a better way to write this answer with some more decimal places, because there are more decimals after this 6, this would continue on from there. What we would have is that this is equal to 6.1035 times 10 to the power of negative 8. All right, so whichever answer you prefer is fine, whether you want to write out all those zeros or if you want the scientific notation version, either answer is fine. both of them represent the maximum error associated with this approximation of the square root of 16.1 using the second degree Taylor polynomial centered at 16 for the square root of x. Okay, and so with that, this was the last example for this video. So if you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.